Great. Hello and welcome to the April Wednesday webinar from the EIA Clean Coal Centre. My name is Benedicta Brox and I'm the Communications Officer here. Our monthly webinars are based on our technical reports, which are available from our website. Residents of member countries and employees of sponsoring organization can download our reports at no charge after a one-off registration. Please visit our website for details. The subject for today's webinar is coal beneficiation. Why feedstock quality is key for power station performance. The report on this topic will be published in May. I will now pass you on to Dr. Ian Reid. There you go.
Right, thank you, Benedicta. And as mentioned, this is on coal beneficiation, that report should come out next month. Coal beneficiation is the treatment of coal to remove minerals and moisture and reduce contaminants in coal, such as mercury and sulfur, and in some cases also to stabilize coal. In addition, in this report, we'll be looking at the manufacture of coal slurry fuels for the direct injection carbon engine, the DICE engine, which is a higher value product. It isn't possible to cover everything today, so for the webinar, we'll consider the relevance of coal beneficiation, briefly review the main current methods practiced in over 3,000 plants, and then discuss some emerging technologies for coal beneficiation. So the next slide. Commercial considerations dictate the current extent of coal treatment and also the demand for high-quality feedstock. Power station designs are usually set on the availability of the coal feedstock, even though that might impact the potential thermal efficiency, operability, and emissions from that technology. A station design and technology selection will be set for a particular coal specification and operate at their best close to that feedstock. However, a high-quality feedstock is needed to realize the full potential of the latest technologies available to new power station facilities, what we call the HELE technologies. Coal power station technology has seen significant advances in recent years in raising efficiency and lowering emissions, but the feedstock can make an important contribution. The quality of the coal affects every aspect of a coal station. But to say quality can mean different things. A high energy content that leads to improved efficiency by avoiding boiling water in the feedstock or heating minerals that form ash. Or it can mean reduced emissions such as sulfur, and that's one of the reasons lower rank coals have become more attractive in recent years, where sulfur was the focus. And part of the reason for the switch to PRB coals in the United States. Well, water in the fuel has the greater thermal load in a plant than the mineral content. The formation of ash can increase boiler fouling that impacts the reliability of a station. Removal of contaminants such as sulfur and mercury can mean simpler pollutant control, consuming less chemicals in the effluent treatment plant. But a fuel with a higher energy content can mean an increase in primary NOx emission. As well as impairing the station performance, transporting low-quality fuels has substantial impact on the mine-to-plant greenhouse gas make. And that's why lignite, for example, is normally used locally. But it's becoming an issue in some countries where there is low coal quality and mines are remote from power plants. The trend to use lower-rank coal has been driven largely by the need to reduce sulfur, but also by unavailability of higher-rank coals. In countries exporting coal, lower-grade feedstock for preparation plants may be consumed locally. New applications are emerging for coal, and the one I'm going to discuss today is the preparation of fuel for a diesel engine, a marine diesel engine, which has been adapted to take a coal slurry fuel. This is a fuel that needs ultra-low ash yield. Although there has been a much publicised decline in thermal power in OECD countries with a shift to gas and renewable generation, there's actually been a small increase in global coal use, driven by countries with rapidly increasing demand and perhaps limited other options. The IEA predict that coal consumption will rise at a modest rate over the next decade. At the same time, for a variety of reasons, the energy content of coal is falling, and that has a direct impact on carbon emission, as there are more energy losses in handling a greater volume of feedstock. Examples shown here for India and the USA show a clear trend of falling energy content in coal, and that leads to higher CO2. The quantity of ash and also the ash composition, the base to acid ratio, as well as causing fouling, can also affect particulate control and may reduce the effectiveness of NOx control technologies. Energy security considerations and a desire to avoid imports can result in an increase in the use of lower grade coal at a time when international agreements seek a reduction in CO2 from the coal power industry. As the quality of coal decreases, there's a direct impact on the ability of plants to meet pollutant limits, and may be detrimental to countries such as India that are implementing international emission standards, seeking to modernise the power fleet, and at the point of making substantial investments in pollutant control apparatus and complying with COP21. The coal industry has to respond to the challenges on emissions, and there will be a significant need for new preparation facilities in those countries expanding the use of coal. In this webinar, we'll look mainly at emerging beneficiation technologies. I've actually got 4 to discuss today. But before doing that, let us briefly look at the treatment technologies that dominate the coal preparation industry. In a way, perhaps this is the most important slide in today's presentation, as this is what is currently practiced. As the technologies applied are familiar to those working in this field, I will just summarize that here, but there's much more detail in the full report. The plants pictured here represent the vast majority of coal preparation plants. These either use wet dense media systems utilizing magnetite to assist separation, and those make up about 85% of the preparation plants. And the remainder are using dry separation technologies that are really suitable for arid regions. The top picture is a dense media unit located at Muglan, Turkey, and shows the main parts of a coal washery with coal supplied from the right and delivered to trucks on the left. The plant separates coarse and small coal particles using a dense media cyclones and passes the fines to a thickener. This particular one doesn't include fine coal separation circuits, which are actually the main focus of development in dense media preparation plants. The lower plant is an FGX separator, targets coarser coal particles. So it's like an advanced destoning system, and uses an air-based fluidized riffling table, and that requires its own dust control. That's really the major issue with these dry systems. The water-based dense media plant is recognized as offering more optimal coal separation, while the dry technique is increasingly applied because of the drought issues. A serious issue for power stations that was discussed in an earlier webinar. It is impossible to go into these well-known technologies in detail here, but the graph shows the rising cost of treatment as the extent of coal preparation rises. On the left-hand side, the process units handle coarse coal particles, while on the right-hand side are the processes for separating minerals from the finest particles. As we move from essentially destoning at $1 to $2 per ton through to intense preparation as needed for the dice, we feel, for the dice engine, the costs rise to around $10 per ton. As we move from coarse to fine particles, then these circles handle smaller proportions of the original coal feedstock. The technologies for separating fine coal and ultra-fine coal are currently based on spiral concentrators and flotation technologies for ultra-fine coal. These are based partly on separating by particle density, but also use particle hydrodynamics and hydrophobicity to separate coal from minerals. The main recent developments in coal recovery are to be found here, improving the separation of fine and ultrafine particles to raise recoveries, but also seeking to minimize waste. The lower the quality of coal that's fed to the preparation plant, then the more material needs to be processed through the plant, so the costs are higher for low-grade feedstock. There's much more detail on current technologies in the report, and given the limited time, for the remainder of the webinar, we'll look at some new emerging technology options that could replace or augment coal preparation plants. The first three of these are focused on removing removing moisture from coal. So let's go to the next one. Yeah, the first of these emerging technologies is a new process developed at Virginia Tech that more specifically uses the hydrophobicity of coal than in a flotation plant. While minerals are hydrophilic, organically based coal is hydrophobic, and that is the key property for separation here. Termed hydrophilic to liquid separation, this new device takes slurry from the medium coal circuit that is fine and ultrafine particles and combines that with a light alkane solvent. The coal particles partition into the solvent, leaving an ash-water mix behind. The lower density coal solvent phase is taken from the top of the vessel, while the wastewater and minerals progress to the thickener. Overhead, the solvent, which is selected partly for the ease of distillation, is then recovered, and this process provides a dry product. So this is a technology that separates the coal from minerals and also dries the coal, avoiding a dewatering step for fine matter, which could be very important in the future. So the potential for the technology to replace spiral concentrators, flotation cells, and water reduction apparatus, simplifying the preparation plant to include fine particles. This next technology is, in essence, a kind of thermal refining. The coal is processed in an oven, and is a method really tailored for coal that has a high moisture level. Termed the pristine M process from Clean Coal Technologies, it's primarily intended to remove water from low-rank coals such as Powder River Basin subbituminous coals. But the process goes further and removes most volatile gases, and also collects coal liquids by heating the coal to around 450 centigrade, which are conditions not dissimilar to those in the first stage of a coking plant. The water is removed, and the lighter gases are used to fuel the dryer, so it's self-sufficient in its energy needs. While the heavier volatiles are collected and could be sold or returned to seal the coal surface to lower the reactivity, stabilizing the coal for transport, and really to deal with the self-heating problem. The process also removes the mercury content of the coal, as that's partly removed with the volatiles components. The main benefit, though, is the reduction in water, and the process aims for moisture levels of less than 10%. The technology is moving currently from the demonstration stage to construct a commercial plant for PRB coals. At the bottom of the slide, I've just briefly mentioned chemical and biodigestion, and the reason that I've included that is that the very low ash technologies were originally restricted to chemical digestion or bio-oxidation techniques. However, the issue with these is the cost of chemicals, the waste streams, and the residence time for bio-oxidation, which can be several weeks. So these techniques are only suitable for higher value products. The next technology we'll look at is from Clean Coal Systems, and again, drying is a core purpose of the technology. But this is more complex, and it seeks to remove a number of components prior to a boiler, using a combination of thermal beneficiation, also not as high temperature conditions as the pristine M process, but adds in a fuel-rich combustion to control NOx and adds limestone to control sulfur in add-on reactors prior to the main boiler. So this is a retrofit technology to upgrade older systems, and but aspects of this technology might have application in new gasification plants. Just looking at the content of the beneficiation, traditional beneficiation side of the diagram. The cold mill conditions are milder than for pristine M, although the gas is coming in around 400 centigrade from the boiler. And the plant is designed to remove part of the mercury and some ash, but mainly water and volatiles. The preparation circuit shown here combines coal and the boiler exhaust gases in a mill, partially removes water, mercury and ash, and supplies dry coal and air to the reactors. The retrofit technology uses external gasifiers designed to penetrate the water wall. So once the coal is prepared and fed to the gasification stage, then a second beneficiation process takes place. The oxygen-deficient conditions in the gasifier prevent the formation of NO, while the addition of limestone converts sulfur to molten calcium sulfide rather than sulfate in the fuel-rich conditions. And that can be removed from the boiler and not pass over the heat transfer tubes. The product gases then progress to the original boiler and burnout is completed there, with the original firing system now used to supply overfire air. The retrofit technology offers a solution to remove much of the pollutants upstream of our boiler, with some of the results obtained in NOx and SOx shown in the yellow box. The back-end treatment may be arranged to further lower the emissions and would require a baghouse to control dust as burnout is completed in the main boiler. It's a revolutionary idea with potential applications for stations that are not easily adapted to meet new emission limits, and has completed its demonstration phase on an old stoker furnace. If we just move to discuss lignites, of course lignites have the probably highest water moisture content and potentially highest ash content of the coals we're currently using. There's been a large effort to find an economical way to dry lignite, and although the evidence is that drying the fuel is the one single measure with the greatest potential impact on lignite plant performance, most lignite is combusted in its raw state. There are two drying technologies shown here. They're both commercially installed at commercial scale, and are both designed to use low-grade heat streams for drying to avoid losing thermal efficiency from the plant. As of course, most plants use the hot furnace gases to dry lignite, detracting from the performance of the station. The first of these commercial fluidized bed dryers then, shown here schematically, is dry fining from Great River Energy. The unit uses waste heat streams, in this case hot water and air, to dry the lignite. This device also has a mineral segregation compartment at the front, so that the mineral and mercury content can also be reduced by specific gravity means. The device has been developed with a final steam section for high moisture lignite fuels. The test data shows significant improvements in efficiency directly from removing the water, but also from other parts of the plant, such as the energy used in milling a more friable fuel and savings from a reduction in the overall gas flow rates through the plant. The other process shown here is the WTA dryer from RWE in Germany, and this dryer is designed to optimize the steam conditions in the dryer and is ideal for lignites with a very high moisture content, up to around 60% of the fuel. The latest designs are using a more moderate steam conditions to reduce the overall extent of moisture removal, as the issue becomes that the plant specification is a limitation on the extent of drying. Now, the last of the emerging technologies I want to discuss is the DICE engine, the direct injection carbon engine, and the preparation of its fuel. This is the DICE engines is a technology under development by Cyro in Australia. Coal slurry fuels are used as direct feeds to boilers, and that is quite widely practiced. And as a direct replacement for pulverized fuels, the main advantage is a reduction in NOx emissions because of the thermal load of the water. The application of diesel engine offers higher efficiency operation, but requires a specialist fuel. The key properties are very fine particles, ash yields of under 2%, and higher fuel density than is normally applied in a coal slurry. And that's obtained by allowing a higher fuel viscosity. Originally, a chemical acid-alkali digestion process was used to formulate the fuel, as that is capable of lowering the ash yield below 1%, but comes at higher cost. The slide shows the now preferred Jameson flotation cell for producing an ultra-low ash fuel of around 2%. The technology has no moving parts and uses a liquid jet downcomer to create a turbulent mixing zone to contact the coal particles, but otherwise uses separation principles for a standard flotation cell. By carefully selecting the feedstock, especially the composition of minerals in the coal, the unit can achieve the revised specification. A number of technical issues have been resolved associated with abrasion, and a more concentrated coal slurry can be used due to the high pressure operation of the injector, which has significant benefits to efficiency and fuel stability. The storage and transport of the fuel is obviously a major issue for a coal slurry technology. The micronized carbon fuel is cost competitive with diesel generation, does require specialist fuel storage, but there's a number of potential applications in distributed energy generation, electrical energy generation. So just to consider some of the points raised today, the development of HELI technologies has seen a dramatic improvement in thermal power performance and reduction in emissions. However, low-quality feedstock with a low energy content can detract from the optimum performance that could be achieved, especially where this is due to high moisture content. Overall, wet, dense media, physical separation technologies are dominant in the industry, but there is a growth in the number of dry separation plants for coarse and small coal due to the effect of water shortages. That is even though wet, dense media separation is more efficient. In developing physical separation, the challenge is to improve ultrafine capture and reduce waste streams. In fact, some old waste reservoirs are now seen as sources of feedstock for these fine particle technologies. We consider some of the new technologies emerging that are primarily aimed at lowering the moisture content of coal, as well as removing ash and mercury. These methods would alleviate the extent of effluent gas cleanup that is needed to meet the latest emission standards. It is only really possible to improve the efficiency of a lignite station, for instance, by drying the feed if the energy used for the drying is a waste energy stream or low energy stream, as otherwise that is taking heat from. We've briefly considered the preparation of fuel for the DICE engine, which is an option for flexible distributed power generation, and perhaps placed alongside a conventional power plant. Not all coal is suitable for DICE due to the tight specification, but recent advances have made the technology technically more attractive. Overall, as the general quality of coal declines in terms of rising water and ash yield, beneficiation has a key role to play, especially in those countries expanding coal generation. The use of poor quality raw feedstock, even if blended to an acceptable specification, will prevent the industry from achieving the clean coal operation that is needed. That's brought me to the end of the webinar, and thank you for listening. And if you want more information on coal beneficiation, then the full report will be available soon. Right. I'll pass back to Benedicte.
Yeah, and thank you for that, Ian. I will just see if we have a few questions. I think we have one. The first one is, what are the key attributes of MRC fuel for the DICE engine?
Thanks, Benedicte. One of the key parts of preparing the fuel is to choose a suitable fuel, and there's a process called coal grain analysis that's used to assess whether a coal is suitable for use in the flotation device. The worst aspects of the minerals composition is high iron or quartz in the coal, as this would abrade the parts in the engine. So minimizing that is a key attribute in choosing the fuel. I think we've got another question here. I have a question. Is there evidence to show how beneficiation of the fuel can reduce the cost of generation at the power plant and the avoided costs of flue gas cleanup, ash disposal, etc.? It's quite a complex question. I mean, obviously, say for a lignite plant, you would have to pay to dry the lignite, but then if installing a new plant, there's a capital cost benefit in the smaller size of the plant. I mean, lignite boilers are normally much larger than standard coal boilers, and so an immediate saving in simply the size of the plant, but also a removal of contaminants in the coal will mean less chemicals are needed at every stage of the effluent cleanup process. So it's I can't answer it in dollars per ton, but directionally, especially for a bespoke plant, you can make substantial savings. I mean, one of the issues in removing a lot of water and ash from the fuel is that the coal moves out of the design specification for an existing plant, and that is the limitation. And in those cases, the cost benefit will be reduced. Yeah. Okay.
Super. Thank you so much, Ian. That's all we have time for, I'm afraid. If you have other questions, you're welcome to direct them to Ian's email on the screen there. The PowerPoint from this webinar will be available for download on our website very soon. The next webinar from us will be on power generation from coal using supercritical CO2, and it will be presented by Dr. Chen Xu on Wednesday, the 24th of May. Thank you all for joining us today, and goodbye.